Hello, my name is Christophe Delinochin, and today I'm going to talk about a flight recorder for C and C++ programs. You can find it at github.com/c3d/recorder. Like a flight recorder in a plane, this flight recorder is designed to record data continuously so that you can understand what is happening after, for example, a crash. Instrumentation that is always there is there when you need it. So why a flight recorder? Did you ever wish you had more information about a crash? Like, my program crashed, but I have no clue why. So I'm thinking, what was I just doing then? Maybe some idiots hit any key at the wrong time, and we know that idiots are outsmarting us. So I wish I could reproduce, but as much as I wish that, sometimes I just can't. What do I do in that case? You all know about Heisenbergs, these mysterious bugs that happen only once, and they like to happen when you're not looking. And even if someone can reproduce, maybe some idiot has better things to do than to reproduce for me. So what happens often is that if the problem has not shown up for quite a while, we close the bug and we hope for the best. That adds to a long list of unsolved mysteries, but more importantly, it makes customers sad because the problem is not solved. So what does a flight recorder bring to this equation? It collects information about problems before they happen. It records information while the program is running to print it, for example, when you receive a signal. Here, I'm receiving a signal information request, like SIGINFO, that I sent from the terminal, and you can see in blue printed the information for events that were happening just before I hit this, I sent this signal. So you record continuously. You can see the record statements there, and this is instrumentation that is designed to be always there and always on. So it's there when you need it. Once it's there, we can do more. Like we can do runtime configuration, for example, to trace events, or we can even do continuous measurements and graphing. One instrumentation that has multiple uses. So how does it work? What is this flight recorder? It's basically a way to continuously record data in multiple secular buffers with log-free updates. You record data continuously in secular buffers, so new data overwrites old data. But you can have multiple buffers recording different types of events at different speeds. That makes it possible to preserve all important records, like the ones in green here, along with the most recent high-frequency events, like the ones in blue here. So how do you use that project? Well, the easiest way is to clone it as a submodule, and then you have one header, recorder.h, and a couple of C files, recorder.c and ring.c. It's designed to work mostly like printf. The record statement begins with the recorder name, and then it's followed by a standard printf style format. That makes it easy to port existing code. Here's an example where the spice info existing macro in spice was rewrote to use the record statements. There are some caveats that I'm going to focus on next. The number one is that formatting happens only if and when printing. So you do not want to record strings that may not be valid at printing time. When you execute a record statement, data is only recorded. It's not formatted yet. The recorder entry contains copies of your data, like a timestamp, the source location, a global order that lets the recorder sort things when you dump them, your format, and then the arguments that you pass to the record. Now, if this is a string argument, we only copy the pointer. We don't copy the string itself. So formatting happens only when the record is dumped, which means at this time, all strings must still be valid. And this is a counterexample where I free a string after recording it. That's bad because the pointer is no longer good. And if I dump the recorder at that point, I get garbage. It's not a problem for C constant strings. Even if I compute the address, both the strings that we see here will be valid at any time during the program lifetime. Another caveat is that there is a maximum of 12 arguments. There are 4 arguments per record entry. You see the args field here has 4 possible values. The existing macros support up to only 3 entries, so that's 12 arguments. Now this is easy to extend, but it's annoying code to write, and I did not find that many use cases for more than 12 arguments. So how do you define and declare recorders? The idea is to have a self-documented description of the recorders that you have in your program, what they mean and how many things you have in them. The recorder macro defines the recorder. It begins with a recorder name and its size, that is the number of entries the recorder can hold together. The last field is used for self-documentation to list the recorders. And you can see an example here where we list the recorders available in the SpiceC program. The recorder declare macro declares a recorder that's to be used, for example, in header files if you want to use the same recorder across multiple C files. So that works like a function declaration. Now, if you want to dump the recorder, that is to list the recorder entry sorted by creation order, you can use the recorder dump function. And that is going to dump a sorted list of your recorder entries across all recorders. There are variants that allow you to select specific recorders to dump using regex. The recorder send function can be used if you want to send the output to something else than standard outputs. Now, the standard output for the recorder is defined by 2 callbacks. One set that is defined that selects how to print the recorder information, and one that is designed to select how to format the recorder entries. And you can also dump the recorder on signals, and the recorder dump on common signals function does just that. The first argument is a bit mask of the signals you want to enable. The second one is a bit mask of signals you want to disable, and value 0 sets a default set that depends on the machine or operating system you're running on. Now, tracing is one of the interesting features of this approach. It lets you trace execution of your program by showing the events as they happen. So you activate traces by giving the name of recorders in the recorder traces environment variable. So for instance, if you set recorder traces equals channel write, then you're going to see all the records being done to the channel write recorder. You can use multiple names separated by colons or spaces, and you can use regular expressions to select groups of related traces, for instance, all traces related to that begin with channel in that case. Applications can also define their own variables and possibly have slightly different behaviors depending on which variable you use. Then, when traces are activated, the record statements executed for active recorders are dumped immediately. This can also be configured programmatically using the recorder trace set function, which takes a regex. So these are 2 examples. The first one enables all recorders that ends with warning, and the second one selects the traces that are specified by the spice traces environment variable. Now, as you can see, the recorder is designed to be configured dynamically. What is interesting is that the configuration parameters are accessible for you, and you can do something else with it. For example, the recorder trace for the GSP queue max length can be used to set the length at which I'm interested in seeing something. So if I set the length to 400, for example, that means I'm only going to see the lengths that are above 400 due to the second test, the test on the second line. You use the recorder trace or alternatively the recorder tweak macro to access the value that is set for recorder. You can use the name equals value syntax to set the new value. So in that case, JSTQ max length equals 400. If you use the name alone, it sets the value to 1. That means you can also disable a trace with name equals 0. For instance, you can disable an annoying warning that way. There is a configurable value which is associated with each recorder and is normally used to enable or disable tracing. But you can use a recorder tweak define to add a tweak that doesn't have an associated recorder. So that means you can have a configurable value that you can change. For example, if you have a min and max parameter that you want to associate for some specific recording, you can do it that way. You can also use the recorder data and export it to another application, for example, for graphing. So this lets you use the existing recorder instrumentation to graph real-time data. The recorder entries will be shown, as you can see on the right. All recorder entries must hold similar values in the same order for this to work well, because otherwise you cannot make sense of the graph. So in that case, we have two records, and they are compatible because the first argument is a floating point value, %f, and the second argument is an unsigned long. And so they both have the same type, and they also seem to mean the same thing, even if the variable name is not the same. Now, when you have a trace like this, when you have a recorder that is configured like this, you can export its contents by setting the recorder trace with the syntax that instead of having a numerical value on the right of equal, has a list of names. And these are the export names of channels for that recorder. So the data is exported to shared memory, and there is an example in the recorder repository, a small tool based on Qt5.9 charts that lets you graph things easily. You use the same names used to export data channels. This has been tested with a fairly large number of entries per second. So the best way to show how this works is to actually use it. So here I have a small program called Spicy, which is a remote viewer using the SPICE protocol. And if I use it normally, this is what I see. It just works normally, but now I can set recorder traces and get some help to know what are the available traces. And this is the documentation that comes out of this. Now, let me take a look at let me export the JSTQ stats. So this is the statistics about GStreamer Q length. And if I just show them, I have data in text format. I made the choice of having a slightly different behavior if I use SPICE traces instead of recorder traces. And you can see the difference is basically that I don't go through the Chili blogger in that case, and there is slightly less data to be seen on screen. Now, I can also use this to export data for the scope. So I'm going to use this name, and then I can launch my scope here and see the data in real time that is dumped from my application. And as you can see, this is pretty fast. I have a fairly large number of samples here. That application by default is configured to take about 2,000 samples, and then it's going to start scrolling. So an instrumentation that you want to leave always on has to be pretty high performance. And codes to record are fast. So this is a comparison between record and other common operations that you can do in a C program, like getting the time of day, memcopy, malloc, snprintf, printf to dev null, or flushing printf to disk. And as you can see, record compares favorably to most of them. As a matter of fact, there are two variants of record and record fast, because the get time of day used to timestamp the record is taking most of the time. So you see that basically recording something is on the same order of magnitude as copying 512 bytes in memory. Now the same thing is true for a MacBook Pro, and I also tested on a Raspberry Pi and second generation Raspberry Pi, which apparently has slower disk memory. Now, for scalability, the flash recorder uses log-free recording. So this means there is no log taken when you store something. It just uses atomic increase and decrease. That means you have pretty good scalability. These are the numbers for 1 through 32 threads on a desktop Xeon. That's the same thing on a MacBook Pro. And these are the numbers on Raspberry Pi. Of note, the numbers that you see there are the duration, the average duration for record across all the threads. It doesn't mean that's the time within one thread. So the time within one thread may increase. And that's an important caveat to remember, because memory bandwidth is the limiting factor here. We are storing everything in memory, and we're not very good with the caching since we keep writing at new locations. So I hope that this project interests you and that you will find uses in your own projects. And if you want to see how this presentation was made, this is the URL for this Dao 3D presentation. Thank you.